What we saw in class the other day was that when f prime equals 0, then you're talking about a horizontal tangent line, of course. So a horizontal tangent line is only going to occur if you're what I call the top of a hump, horizontal tangent line, bottom of a trough, horizontal tangent line, or what I call the little zigzag, right, where there's not a local max nor a local min, but the graph kind of flattened out for a moment. There's that horizontal tangent line. And really what's the same case is if it just comes down this way. So let's just say there's only 4 instances where you're going to have a horizontal tangent line, and the graph is going to look like one of these 4 instances anytime that f prime equals 0. That's a really valuable piece of information, and don't forget it. The other thing you want to consider is that when f prime is greater than 0, so I can see where this discussion is going. It's going to end up being a little review before I actually do the example, so be it. When f prime is greater than 0, this means that f is increasing. And you can see that anytime you have a function that's increasing from left to right, then all the slopes of any tangent line that you put on there, or I should say it like this, any tangent line you put on there is going to have positive slope. Even if this thing were like this, any tangent line you put on there is going to have positive slope. In other words, the derivative is positive when the function is increasing. Similarly, if f prime is negative, then we're going to find that the function is decreasing for essentially the same type of thinking here. Here's a decreasing function. Every tangent line I put on there has negative slope. In other words, the derivative is negative. Similarly, if the function were coming down like this, every tangent line I put on there has negative slope. The function is decreasing. Now, this next notion is a little sneakier, and I don't know that I'm going to really so much go into the details right now. I'd rather just do it on another video so we can get on with the example here, which most of you would prefer I do, I bet. When f double prime is greater than 0, then that tells you that the function is concave up. In other words, it's got this either increasing cup up look or decreasing cup up look. That's concave up. I'm not going to go into the description of it right now. It's a little bit more of a long-winded description. A lot of people don't quite catch it the first time by. I'm sure a bright group such as my present 1A group would get it no problem. But I'll talk about it in a future video very shortly. When f double prime is negative, then that tells you that the function is concave down. In other words, it's decreasing concave down or increasing concave down, but it's concave down. So the other thing we got to remember here is that an inflection point, that's going to be where the function changes concavity. And, whoops, kind of went off the screen there for a minute. For instance, look. See right here? This is an inflection point because to the left of it, we're concave up, and to the right of it, we're concave down. Another one right here. To the left of it, we're concave down, but to the right of it, we're concave up. These guys are called inflection points. We'll find that these inflection points occur where the second derivative equals 0, but the reason I don't really talk about that so much is because sometimes the second derivative will be 0 and it won't be an inflection point. So it's better just to define the inflection point as a point where f changes concavity, either from concave up to concave down or from concave down to concave up.